my talk today is about the, semi-classics, the, in some sense, proper use of semi-classics and resurgence in quantum theories. So I will start with some general consideration. So when I was starting to think about these topics, I heard the talk from Mike Douglas. This talk he gave on foundations on quantum field theory in string math. And the question that he was addressing was, can we make sense out of quantum field theory, or whether there is a continuum definition of quantum field theory? And his starting point was that we can actually construct Euclidean functional integral. There is no difficulty there. But the essential difficulty in rigorously defining, and there is no essential difficulty in rigorously defining a Gaussian functional integral and setting up perturbation theory. So one can construct perturbation theory. It doesn't matter if you are doing PET integral in quantum mechanics or PET integral in field theory. Formally, this procedure will define for you perturbation theory. But he said something like, the major difficulty that most mathematicians feel uncomfortable with this is that QFT is still not rigorous. It's that because the standard perturbation theory only provides an asymptotic divergent expansion. All the expansion that you will get from a generic quantum theory are asymptotic divergent series. And these series have and if we want to define quantum field theory properly, to begin with, we have to be able to define the meaning for these divergent asymptotic series. By the way, feel free to ask any question during the talk. Please interrupt as you wish, and I will be happy to answer them. But actually, the situation is even slightly worse than he described. This is an isolated problem in the list of problems that we face in standard gauge theories. For example, if you take Yang-Mills or QCD or super Yang-Mills, it doesn't matter. Let's say n=1 super Yang-Mills. You will face some number of problems. These problems are also there in, for example, two-dimensional gauge theories, or it doesn't matter, two-dimensional theories. As I said, perturbation theory is always an asymptotic divergent series. This is true even after regularization and renormalization. After making term-by-term finites, if you look to large order behavior of the perturbation theory, it will generically be a divergent series. One question is whether there is a meaning to perturbation theory. One can give meaning to this structure. Another question, for example, in Yang-Mills theory, the so-called semi-classical dilute instanton gas approximation is neither semi-classical nor an approximation. Actually, this dilute instanton gas in gauge theories, you may read these words in books, but what I am telling you is that this sentence as a whole here is meaningless. So this dilute instanton gas assumes that the separation, inter-instanton separation, is much larger than the instanton size. But in these kind of gauge theories, the instanton size is a moduli. So you can take the moduli anything you want, and there is no meaning to the assumption. So, the size may become larger than the separation. So this whole thing it is not clear what it means here, at least in the standard formulation of gauge theory. If you ever read Coleman's lecture, there is also a statement he calls infrared embarrassment. If you look to contribution of large instantons to, for example, vacuum energy, they are IR divergent.
IR divergent are just tells you that you are doing something terribly wrong. They should not be there. So this is, he refers to it as infrared embarrassment. And if you are in a theory in which you have a control over large n limits, for example, something like sigma models, okay, something like CPN in 2D, you have control over the large n limits, then you can show that actually the large n results are incompatible with the instanton results. And this should better be so because we trust these large n results, but to instanton results, we shouldn't trust. Okay, they are not correct the way they are formulated. There is even a deeper problem, which is referred as renormalon problem by 't Hooft in 1979. I will not explain it right away. I will explain it when the time comes, or may not be able to explain it throughout these lectures, okay? But this is a deeper problem. And according to actually Resurgence, these 5 problems here are not independent. And the only thing that was referred in the Douglas's lecture was just this thing here, this problem there. So these problems, according to, more properly done semi-classics and resurgence theory, these problems are interconnected. Okay. So now it had been almost 10 years with the involvement of this resurgence and trans-series idea in quantum theories. So at the time, at the time these were new ideas, but now they are a decade old. So, but we can still call them recent in the grander scheme of things. So the tools that I will talk about in these lectures, part of it are tools from, let me say, from math side of the story. And part of it are new ideas from the physics side of the story. So from math, I will describe for you resurgence theory and trans-series a little bit. And from the, and also something called complex Morse theory. These two are intimately related. The idea of complexification of path integral. And as I say, these two are tightly connected to each other. One of them is like geometry, the other is like analysis. Okay, for the same thing. And I will show you this in simple examples, at least in simple examples. And the thing that comes from the physics side is the idea of adiabatic continuity. This idea is the idea that one can connect strongly coupled, incalculable regimes to weakly coupled, calculable regimes. This is a very difficult thing, but in the last 15 years, this is a story of almost like 15 years or so. It is understood that we can do this in many gauge theories in 4 dimensions. And in the last lecture, I will describe semi-classical computation on R3 cross S1, on small s1, and show how they are continuously connected to large S1. This is not a thermal S1. This is different setup from the thermal construction. Any questions so far? This is the general setup. Okay. So let me start with the basic structure of perturbation theory and tell you some standard things about it. So every student learns some amount of perturbation theory, starting, for example, in various classes, but you know, first probably in standard quantum mechanics class, you know, we learn some generic problem with some coupling lambda that we do evaluate, let's say, some spectrum like energy. We do usually do, you know, first order in perturbation theory, second order in perturbation theory. We hardly do any third order in perturbation theory in the quantum mechanics class. And in the standard Rayleigh-Schrödinger perturbation theory in quantum mechanics, things seem to get better in the first and second order perturbation theory. And an interesting fact is that this sum, if you proceed further and further, at first it starts to get better and better. But eventually, if you ask the ultimate question that what happens at the end game, how does at very large order the perturbation theory behaves, almost always this coefficient here diverges factorially. So that means that regardless of how small lambda is, n factorial, you know, it's like n factorial will always win and will render this series divergent, okay? So then the conclusion is that perturbation theory yields divergent asymptotic series. This is the standard conclusion. But on the other hand, perturbation theory is an extremely successful framework. How these two last statements can be compatible with each other? Okay. So let me first show you that perturbation theory is immensely successful. For example, if you look to QED, quantum electrodynamics, for magnetic moment of an electron, this is one of the best theory experiment agreement ever. So this is the anomalous magnetic moment of the electron. It is developed up to disorder in perturbation theory. This is alpha is the fine structure constant, your expansion parameter in the game. If you plug this result to, you know, if you plug in this result, fine structure constant 1/137, you get this result. And experimentally, the result is this. You see that 1, 2, 3, 4, 5, 6, 7, 8, up to 11 digits, there is an agreement between experiments and theory. It looks like there is no problem here, you know, theory is agreeing with experiment to a tremendous precision. Similarly, if you look to beta function of quantum chromodynamics, QCD, these are the points are experimental result for the running coupling, and this yellow solid curve here is the theoretical result for the running coupling. There is a quite precise agreement between the two. So this just tells you that perturbation theory works. So, but on the other hand, the problem I am referring to does not exclude this. So if you, let's say this is some exact physical result, okay? Then you started to do perturbation theory. First order, second order, third order, fourth order, fifth order, so and so on. So the situation up to some critical order and gets better and better, tries to approximate the exact result. But after some point, it blows up, okay? So it gets better and better approaches, and then it blows up. Let me call this axis here error. Error is, let's say, exact results minus perturbation theory normalized according to exact result. Error gets smaller and smaller and smaller up to an order n star, which is dictated by your coupling.
So if this is fine structure constant, then the error will get smaller and smaller up to order 137. But after that, the error starts to blow up. So this is the traditional view on the asymptotic series. Now, this fact, the fact that asymptotic divergent series has this behavior, there is a critical order, this one, up to which, you know, perturbation theory tries to make things better and better and better. And there is an order, optimal order, that the error is minimized, is a brilliant realization of Stokes. And this is, his realization is in the context of the Stokes phenomena. And is the standard argument is that there is an optimal order at which error is minimized. This thing, the fact that error is minimized at this order, which is dictated by your coupling, which is 1 over coupling, it turns out to be very deep statements because of the following reason. Okay, let me say one more thing. Stokes, his idea is to truncate the series when the error is minimal, and this thing is called this term or optimal truncation. And he accepts that perturbation theory can never do better than this. This is our error, okay? This is error. And perturbation theory will never be able to achieve anything better than this, okay? But this error, the thing that we call error at this stage, physically turns out to be very interesting and very deep. If you calculate the error, the term that the error gets minimal, and if you try to quantify the error, you discover something very interesting. Error is you are truncating the series at order n star, and the coupling is lambda, and lambda raised to the power n star. So use Stirling approximation for n star factorial. This is standard Stirling approximation. It's n over e to the power n, and use n star being of order 1 over lambda. So you get here from exponential n star, because this thing cancels with that thing here, and the only thing that remains is this part. And you learn that error is actually exponential minus 1 over lambda. This is very interesting because this is something that we would call non-perturbative, okay? So you learn that the error in perturbation theory is something inherently non-perturbative. So this exponential minus 1 over lambda is something that you cannot expand to a Taylor series around 0. For example, if you try to do that, you know, put 0 here, you will get exponential of minus infinity 0 plus 0 plus 0 up to infinity. Okay, so actually this thing is inherently different from perturbative structure. Perturbation theory is an expansion in lambda, but this thing here cannot be expanded to a Taylor series in the coupling lambda. So this is one reason that, you know, non-perturbative aspects of quantum field theory are discussed in different sections than perturbative aspects, okay? Any questions here? Okay. So there is actually, it turns out that there is something even deeper in this story. And this deeper observation is also due to Stokes. Stokes observed that this thing, which he called error, inherent error or inherent vagueness, he observed that whatever, he was working with exponential integrals, and the particular thing that he was working with was Airy's famous integral, which shows up, for the behavior of light near caustics or in the discussion of the supernumerary rainbows. This was the physical problems he was addressing. And this Airy's integral is a standard exponential integral with multiple saddles. Okay, he observed that there is another saddle in the problem, and its contribution is just this non-perturbative factor. So this is actually interesting. Now, you did perturbation theory, you did this least term truncation, you accepted there is an intrinsic vagueness of perturbation theory, but this thing is related to some other global feature of the problem, the fact that there is another saddle in the problem, and that saddle's contribution is like exponential -1/λ. This is very interesting because you were trying to do something about perturbation theory, and you come to realize that there is something deeper in perturbation theory. There is knowledge about non-perturbative physics. So I am telling you a little bit at the qualitative level, these historical facts. But oddly enough, actually, Stokes realized this story around 1850s, okay? Maybe 1850s to 1860. But I think his contemporaries did not understand him well. Nowadays, if you look to literature in quantum field theory or string theory, it is full of discussions of various Stokes phenomena. It is part of the, very intense part of the story. But Stokes phenomena was not something, its importance was not understood for a very, very long time. There were very minor improvements. And then, however, almost 100 years later, Dingle, who is actually advisor to Michael Berry and House, this is the same family tree. This is the Berry student, and Berry is Dingle's student. These three started to understand some interesting things about these asymptotic divergent series, some very important things. But independently, French mathematician Jean Écalle understood great deal about the structure of the late terms in perturbative expansion. He was working with nonlinear ordinary differential equations or nonlinear partial differential equations, a different story, but he was trying to understand the structure, the general structure of perturbation theory. And I think he made immense and deep contribution to the subject. And the name Resurgence is due to him, actually, and I will tell you its origin, why he referred to it. It's a very deserved name, actually. But I can describe for you the story discovered by Berry and Hals in a concrete story that every student should work out its details in his or her private time. And I will tell you about it concretely. So I will show you the calculation in some detail. Now, but I want to make one more remark. This thing that we call error or non-perturbative in this asymptotic expansion is not just a mathematical curiosity. Many interesting facts in nature is related to these non-perturbative phenomena. For example, the standard tunneling in quantum mechanics is such exponential -1/, okay, let's make this thing, these exponential -1/λ effects. If you go look to Ben's structure of solids, superconductor, or even if you think about your body mass, which comes from dominantly from protons and neutrons, it is generated by these non-perturbative effects. Or if you are a more formal person and interested in D-branes in string theory, it's again an effect of this nature. So this thing that we would call error in perturbation theory, is extremely important, and it is these non-perturbative effects, and non-perturbative effects are at the root of many interesting and diverse phenomena in nature. Any question at this stage? I will go to a concrete discussion, concrete problem. By the way, Rich, students are able to ask questions, right, from the room?
Yes, obviously. And in fact, good. I'll even set the example by asking a very fundamental question. I mean,
sure.
There are, for example, QCD, we believe, has a natural non-perturbative extension. I believe even the lattice is a correct non-perturbative extension.
Yes,
bunch of limits.
That's correct.
But now QED may not have any adequate non-perturbative
that's correct.
extension. How do you distinguish? I mean, both of these things have divergent perturbation theories.
Oh, okay. Actually, this is independent of their structure of perturbation. QED is not UV complete, but QCD is UV complete. So we can formulate QCD on the lattice as a well-defined theory. But even on the lattice, if you look to the perturbative structure of lattice perturbation theory, it is still asymptotic divergent expansion.
Right. So if you're just very dumb and you just look at the two perturbation expansions side by side, would you notice this, or do you have to do something more clever?
Actually, the answer is yes, but it is slightly beyond the scope of this lecture, but I can tell you two phrases. So for QCD, it is probably I should tell you privately because it will not make any sense to students. But the point is, I can tell you, in the Borel plane, there are singularities. In QCD, IR renormalons are positive on the positive real axis. But for QED, UV renormalons are on positive real axis. This fact tells you that QED is UV incomplete. Yes, you can actually say something about this problem by just looking at the structure of perturbation theory. IR renormalon is a problem about
don't let me derail your lecture. Go ahead.
Let's assume that I did not say anything about this question. It's a deeper question. I can maybe address it in the last, maybe slightly in the last lecture. But now let me go to a simple example. Some exponential integral from ordinary exponential integral from minus pi over 2 here to pi over 2. There's a 1 over coupling up front, some sine square. I could have chosen some other, polynomial, some polynomial potential here. It doesn't matter. So if you look, let's say this is the fundamental domain of this integral. And if you look to saddle points, so let's say this is f of x. You find the saddle points by setting df over dx to 0. So this will be sine x, cosine x. So the two saddles will be at 0 and pi over 2. And around 0, this is a Gaussian. This will behave like exponential minus x squared. And here, if you expand this, there will be a contribution of the saddle, but the fluctuation will be exponential plus x squared kind of thing. So there is this saddle and this saddle in the problem. Okay, so this is a two saddle problem. Now let us do the following. Let us develop perturbation theory. We can develop perturbation theory around either saddle. Okay. Let me first develop the perturbation theory around saddle 1. It doesn't matter, okay? And I put here II bar because it will be related to, when we go to quantum mechanics, to something like instant on anti-instant on critical point. But let us not bother about this. So we can easily develop perturbation theory around a given saddle. So you just keep Gaussian part here and expand to x to the 4, x cube, x to 4, x to 5, then make a series of those things, expand the exponential, and find the structure of the perturbation theory. So this saddle 1, if you look to contribution at pi over 2, the contribution of the saddle itself in sine square, if you replace pi over 2, it will give exponential minus 2 over lambda. This part is the contribution of the saddle, okay? And there are fluctuations around it, and fluctuations are encoded here. And if you do the integral over these fluctuations, you will get a series. Now look at this series. So there is one, this is leading order in steepest descent or saddle point approximation. And if you expand the integrand, it is exponential in lambda, then you will get a series in lambda. You can do this on your own. I give this as a homework question in my QFT class when I start discussing perturbation theory in quantum field theory, okay, as a toy example. So you see that there is, if you look to structure of the perturbation theory around saddle 1, there is this non-perturbative piece. The square root of 2 pi is coming from integration of the Gaussian, okay? And then there is this series. And the thing you should realize is that the coefficient here, I didn't write many of them. I just kept it 5th order, but you can evaluate this at any desired order. It starts to grow, okay? It starts to become divergent and asymptotic. Now, let us look to perturbation theory around the other saddle, these perturbative saddles, okay? Here, saddle is at 0, so the saddle contribution to action is 0. So, if you set x equals 0, it is 0. Sign is 0. And then you can develop perturbation theory around that point. And perturbation theory gives you something like square root of 2 pi. You can develop this perturbation theory 1 plus 1/2 lambda plus order. It goes something like that, okay? I just wrote it from memory. But here's the point. This is a standard perturbative expansion around perturbative saddle. If you look to large order behavior of these coefficients here, you will realize that it is actually an asymptotic divergent series. The coefficient here will start to diverge as m factorial. But pretty soon, if you work this out systematically, you will realize that this is not a meaningless divergence. If you look to how it diverges, okay, the overall prefactor here is this thing here. If I call action of the first saddle A1 and action of the saddle I call zeroth saddle A0, the way it diverges is controlled by the difference of these actions. This A10 is actually A1 minus A0. Okay, so this is like, in some sense, something like instant on action in quantum mechanics. More precisely, it's instant on anti-instant on action. But here, in ordinary integral, this is the difference of the actions of these two critical points, okay? So the rate of the divergence, n factorial, there is an n factorial there, and it's divided by this A10, and A10 is the action difference. So the rate of the divergence knows something about other saddle in the problem. Okay. So this A10 is very important because it's really the action difference between two saddles in the problem. And as I said, students should show this on their own, study this perturbation theory. And you can actually show that there is an n-1 factorial, then there is n-2 factorial, n-3 factorial. And so these subleading divergences, if you look at them, you discover something striking. So the structure is as follows. So for n-2 factorial, the coefficient is, there is A10, a factor of A10 appearing in the numerator, but there is this factor of -1/2. Let me put it -1/2 here, plus 9/8, minus, 75 divided by 16. You realize that these are early terms of the perturbative expansion around first saddle. Look, this is very interesting. This part of the story is an information about first saddle in the saddle. Okay, let me call this saddle 2 in the problem, and this is saddle 1. Okay, this is perturbative information and early terms in the perturbative expansion around this saddle. Okay, and this stuff here, let me clear it out. You look to late terms of perturbation theory around the usual perturbative saddle, you see that the rate of the divergence is controlled by the action difference. Also, early terms of the perturbation theory here, let me clean this out, dictates how the things blows up, how the things diverge. So you learn something very interesting, actually. You learn that divergence of the perturbation theory is not something meaningless. It is actually some sort of coded information. Secret form, it has data about regular perturbation theory around some non-perturbative saddles. You look to the perturbation theory around non-perturbative saddle, and the rate of the divergence of the regular perturbation theory is a coded information. Now, this attitude is very different from standard physicist attitude. Standard physicist attitude is that, you truncate the series here, and you do not care about this part that the series diverge. But now, more precise statement tells you that this thing that is usually thrown away and not considered at all is actually, which is this part, it is actually coded information about perturbation theory around the non-perturbative saddle. Okay, this is actually, oddly enough, this story in the ordinary integrals is discovered only in the 90s by Chris Hals and Michael Berry. It's very interesting, in the scale of things, thinking that the, Stokes' work was in the 1850s. It took such a long time to realize this more precise structure in the ordinary integrals. It's quite striking. Now, actually, there is a talk by...
Can I ask a question? Can I ask
Sure.
a question, please?
Yes, please.
Hi. So in QED, what would be the analog of the first series that you have here, which you have given as a homework problem? In QED, what would be that?
So in QED, this is a relatively simple example. This example.
Yes, of course.
So in QED, there can be these exponential factors depending on lambda, and there can be factors involving logs. So logarithms. So in QED, for example, for the perturbative expansion, so we will get a series like this, but in terms of lambdas and maybe involving log lambdas.
Yes, yes, yes. I was just asking about what would be the analog of this other saddle point in QED.
Very good, very good.
That was what
And
I was asking.
This is related to something called UV renormalon and IR renormalon. And it is still, for me, it is still the next layer of things. I will come to those things around the last lecture. But I wanted to describe things for you at this stage in simple terms.
Okay.
So this lecture is about ordinary exponential integral, but you will see that and next lecture will be about quantum mechanics, and the last lecture will be about quantum field theory. So we will come to that. But the answer to your question is that the other saddles, well, yeah, they will be related to this renormalon issue of 't Hooft. And actually, concerning so in ordinary integrals, at least in the ordinary integrals, there is everything is characterized in terms of standard saddles in the problem. So it is a little bit simpler. Also in quantum mechanics, for example, things like double well potential, things are characterized in terms of saddles, standard saddles like instantons or something called critical point at infinity, which can be interpreted as an exact saddle, like instanton, anti-instanton. Textbook says that they are not exact saddles, but you can make them into exact saddles. They are called critical points at infinity, and you can characterize these other saddles in terms of these objects. So there are really two categories of objects in quantum mechanics, instantons and critical points at infinity. And in QFT, things are a little bit more involved. This requires some physics input as well, and to go to a semi-classical regime. But I can address that, but it will be the last lecture probably. But I just want to mention this. There is a series on, there is a lecture by Michael Berry. Okay, this is Michael Berry. From 2004, and it's available on YouTube. And I strongly recommend to students in the audience, even senior people, if there are any, to watch this talk. It's a beautiful talk actually, and it captures many of the history of the subject and many of the. And some of the words I actually borrow from him. He says, a divergence series is not meaningless or a nuisance, but an essential and informative coded representation of the function itself. So, and he also refers to this recent progress in QFT and string theory. But he ends up his lecture saying that here in quantum mechanics, QFT and string theory, the technical difficulty is much larger because these are not just a single integral, double exponential integral, multiple exponential integrals. At the end of the day, lattice gauge theory is a multiple exponential integral, but the number of integrals scales with the volume. This is a remark for Rich. But even in those integrals, but in the field theory, we have integrals with infinitely many variables. And Michael Berry ends up saying that things could well be different there. But things work out to be very similarly. And I will show you just one slide, and I will come back to this. Actually, I think this is quantum mechanics. Probably this is for double well potential, okay? So you can do perturbation theory for the ground state. This is actually a standard example in quantum mechanics class, and the first order and second order perturbation theory, okay? But we will do this in the second lecture, but I want to tell you that something I told you about ordinary exponential integral goes to path integrals in quantum mechanics, This is an example for double well, but so if you look to large order of perturbation theory for harmonic ground state here, H bar omega divided by Q, it's a simple harmonic oscillator at the minimum at the, if you approximate at the harmonic level. And then you can do perturbation theory around it. This is level number 0. You see that the perturbation theory is asymptotic and divergent. It diverges as m factorial. And the coefficient, the prefactor here is actually a 2 instanton factor, instanton, anti-instanton. Okay. And it's very interesting. The rate of the divergence is dictated by instanton action. Then you can go ahead and look to not n factorial, but n minus 1 factorial, n minus 2 factorial, so on and so forth. And you discover these coefficients, how it diverges at subleading orders. Now, actually, as I said, you can make in textbooks, it's usually said instanton, anti-instanton are not saddles, but you can actually make them into a genuine saddle. It's something called critical point at infinity. By regularizing the theory, you can put quantum mechanics on a circle, instead of quantum mechanics defining it on R, Euclidean time being on R. You can make Euclidean time on S1 beta, and you can actually, in this context, make instanton, anti-instanton into an exact saddle. And there is good reason to call it critical point at infinity. And the contribution of the instanton and anti-instanton, it has a real parts, and it has also some imaginary ambiguous parts. And it is, of course, proportional to exponential of the 2 instanton. And you can also develop perturbation theory around this thing. And actually, this leading term is something that was discovered early on by Bogomolny and Zinjustan, even before the work of, Berry and Howells. But the fact that there is a very intricate relation, even including these lower order terms of expansion around non-perturbative saddle, order G, order G square, and the large order asymptotics. This is something I showed in a work in 2014 with Gerald. And a question is, so it tells you that there is a very intimate relation between perturbation theory around the perturbative saddle. For example, in this context, perturbative saddle is here, and something like instanton, anti-instanton, and instanton, anti-instanton is a configuration. I will show this later in detail, but instanton is a configuration which goes from here to there, and instanton, anti-instanton goes there and comes back. This is a critical point at infinity. It's a classically forbidden path. So this thing tells you that there is a relation between these two. But I want to explain to you why all of these things are happening. And I want to provide both a perspective from the, both a geometric perspective and a perspective from the side of the analysis. So I think this is a very nice quote by Jean Eccal. He says, let's read this because it's interesting and it really captures the essence of the argument. These things are like critical points in this picture. These things are critical points, and these circles are supposed to describe fluctuations. And he says something like resurgent functions display at each of their singular points a behavior closely related to the behavior at the origin. Loosely speaking, these functions resurrect or surge up in a slightly different guise, as it were, at their singularities. This is just a statement that you are looking to another saddle in the problem, and these are the coefficients of the perturbative expansion there, and you are looking to perturbative saddle, and large order asymptotics of perturbative saddle is completely encoded into the other saddle, both the action as well as perturbative coefficients. I hope, you know, the students here find this relation quite striking, because this thing will be part of a bigger story. It will allow us to define PET integral in a meaningful way, at least in some quantum mechanical cases. Okay, so now let us ask the following question. Assuming that a quantum field theory, this is a big assumption, okay, has some sensible semi-classical regime. And in QCD, for example, on R4, it doesn't. But maybe in some other topology, in some other space-time, it may have meaningful semi-classical expansion, okay? So assuming that a semi-classical approximation is sensible, can we make sense out of semi-classical expansion in a quantum field theory? But if you look to expansion of some observable in quantum field theory, generically there will be, or in quantum mechanics, it doesn't matter, there will be perturbative terms, there will be instanton factors coming from here, there will be some logs, and for simplicity I drop these logs, and there will be fluctuations around instantons, okay? Now, there are some good news and bad news, but even the bad news in retrospect, after understanding things properly, turns out to be good news, okay? It turns out that not only perturbation theory is asymptotic and divergent, actually all series appearing here are asymptotic and divergent. So this structure is called, you know, this combined structure is called trans series. And I didn't write here, there are some trans series coefficients here. Maybe I inserted implicitly here. Let me call this, let me put some star here. Trans series coefficients should be star there. So you can make, you know, you can make this expression well-defined under analytic continuation of the coupling constants. So in some sense, you can understand this object, not just like some asymptotic series, but just like regular analytic function. In some sense, this is the virtue of this structure. It is well-defined under analytic continuation. So, and it is in some sense, an honest representation of the function. Sometimes we may not see what the function is, but the claim of resurgence is that this object is the characterization of the function. Okay. Now, I will tell you, okay, two things. One of them will be the standard perspective, something called Borel transform and Borel resummation. But I should tell you this, when I was learning about this Borel transform and Borel resummation, I understood what it was, but it was also a little bit like magic, you know. It sounded like unjustified magic, but it is nonetheless correct, but it is not immensely clear why it works, and the intuition behind it is quite vague. However, I will tell you two stories. One of them is actually they are not stories; they are math. So one of them is related to analysis. And the second part of the story will geometrize. Geometrize what I told you on analysis. And it is related to things like Stokes phenomena and these steepest descent, left-shade thimbles, and stuff like that. These two things are tied to each other. But if you ever learn something like something related to asymptotic series from the books, first few things will be the following. Let me tell you what they are, but then I will geometrize that story and make it more intuitive. So as I said earlier, the series that you face will be some asymptotic divergent series. This coefficient here will diverge as Q factorial. So Borel transform does the following. It takes the coefficients here and it maps these P of G squares to Borel transform in this plane T. It divides the coefficient to Q factorial. Then you see that this series becomes something like regular, some nice expansion which has a finite radius of convergence. Then you take this Borel transform and you apply to it a Laplace transform, Laplace to PPT. So this is the Laplace transform, okay? If this Borel transform BPT has no singularities on R plus, this is R plus, R plus. So if there are no singularities in this direction, this integral is well defined and convergent, and it will actually give you the physical answer. But generically, this object here will have singularities on the positive real axis. Okay. So this integral will not give you a unique answer. Actually, it will give you here, okay, if there is no singularity, there is a unique answer, and this is the Borel resummation. It's the physical result. But if there is a singularity, something like this, you can do this integral, but it will give you multifold ambiguous answer. If there are n singularities here, okay, there are n singularities, it will give you 2 to the n fold ambiguous answer. Let's say there is only one singularity, okay, just this one. So in this Borel transform, you have to choose a path. You can go above this singularity or below this singularity. The results, you are just trying to give meaning to perturbation theory. The result will be, there will be a real part, but there will also be an imaginary part, but the imaginary part will be twofold ambiguous. And from here on, there will be another twofold ambiguity, and you can choose various paths, things like this, things like that, and so you see that there are 4 ways of choosing paths if you have actually 2 singularities, and it will tell you that this summation will be 4-fold ambiguous, okay? But if you have only one singularity, it is 2-fold ambiguous. Actually, this is a weird situation because to begin with, we had something divergent and asymptotic, and we thought it was meaningless. And now the end product, we did something, we got something finite, but the result is multifold ambiguous. So it still doesn't look quite meaningful, okay? But the interesting thing is following. If you consider, for example, a quantum mechanical example, this imaginary ambiguous part, by the way, quantum mechanics for stable systems, just regular double valve or some periodic potential with no, instability at all. So that there is no room for really any imaginary thing or decay, okay? Genuine, stable quantum mechanics with real spectrum on the of the Hilbert space. You will see that the perturbation theory gives these imaginary ambiguous parts, and these are multifold ambiguous. But the interesting news is that this imaginary ambiguous part will be related to instantons, more strictly instanton, anti-instanton. Now you see that depending on your choice of this Laplace transform, you know, either you choose C plus or C minus, or here in more general case, C plus plus, C plus minus, C minus minus, C minus plus in an obvious notation, okay? There will be different ambiguities, okay? So you see that the result is not unique. There is multifold ambiguity in the results, okay? And if you look to how the result changes, there is a discontinuity in the results. You know, for example, if you compare this path to this path, you see that between these two, summation using this path versus summation using this path, there is a discontinuity between them. And discontinuity are some non-perturbative factors, okay? They are dictated by these contour integrals, okay? And this plane is called Borel plane, okay? So let us summarize what we did. We had some perturbation theory around some saddles, preferentially perturbative saddle, perturbative vacuum. We did some Borel transform. Then we did some Laplace transform, but we generalized Laplace transform to directional Laplace transform. We actually put some angle here so that we allow ourselves to go above the singularity or below the singularity. Okay. And then this gives a Borel sum. So if this direction is a direction in which there are no singularities, then Borel summation gives you something finite, meaningful, and nice. But in physical problems, usually there will be singularity in the physical direction. For example, in quantum mechanics, you have to consider this direction, and there will be some singularities. In quantum field theory, there are singularities here and there. Even in some quantum mechanics example, there may be singularities here and there and in some other directions, okay? But if it's a singular direction like this one, it naively looks like we traded one pathology, divergence of the perturbation theory, with another pathology, which looks not good. It looks like we didn't gain much, except to realize that the ambiguity is related to another saddle in the problem. But this is where things start to become very interesting. Now, this is the standard analysis. Now, actually, what I will do next,
Can I ask a question?
Sure,
Excuse
of
me.
course.
Can you go back to the slide where you discussed the double well potential?
Okay. I didn't yet discuss double well, by the way. Yeah, this one?
Oh, yeah, this one. Yes. Yeah. So I had this question actually. I mean, it's a naive question, but the first series is around the trivial, the ground state, the perturbative ground state.
That's
and
correct.
The other one is the instanton related. Now I have the following question: that suppose I don't have a double well, but I have three wells. Means now. So the second answer, how will it match with the first one then? Because actually, now the instanton structure is different.
This slide was just to tell you that in this problem, there is infinitely many coupled exponential integrals, but the whole thing still works. next lecture, I will actually discuss multiple quantum mechanical cases. One of the cases I will discuss is actually triple wells.
Okay.
Okay.
Thank
so
you.
I will address your question.
Okay.
But
Thank you.
I believe that there is tremendous insight gained by studying just exponential integrals. Because of that, I wanted to devote this lecture to exponential integrals. So I will come to the question you are raising for the triple well potential in the next lecture. And I can assure you, it is full of surprises.
Hello.
Yes.
Thank you.
Thank you.
Can I ask something?
Yes, of course.
If you could go back a slide, is it easy to see that the ambiguity is only in the imaginary part?
Say that again.
Is it easy to see that the Laplace Borel resummation gives an ambiguity only in the imaginary part when the poles are on the real axis?
No. Actually, you can do this directional Laplace transform depending on your physical problem in any of these directions, here, there. But even if you are doing, let's say, let me clean this up. Even if you are doing it in some other direction in connection to another physical problem, you can go around this way or some other ways. So, but the fact that, even, the fact, the data about the saddles in the problem is actually encoded into this Borel plane. Tampons, or there can also be some completely complex saddles. This would be, for example, a complex saddle which doesn't contribute to observables, but it changes the structure of the perturbation theory. But if you want to understand the detailed structure of the perturbation theory, you have to also look to things like that. Okay. So this case is physically very interesting, but the other cases may also be physically very interesting. It depends.
So is the problem being transferred to saying like what is the underlying principle by which you choose that contour to integrate? I mean, in some sense. Like we have like at each
contour
pole
of
we have
path integration, a contour of path integration, or contour in this Borel plane.
Yeah, I mean, like as you said, at each pole I have a twofold degeneracy as to degeneracy, but like an ambiguity as to whether I traverse it upwards or downwards.
Yes.
So the so to say correct path is, I mean, how do I find that for a particular...
Okay. I will tell you. The end result. I will tell you. The end result will not depend on the paths. I will come to that. I just told you the pathology of when you do Borel resummation, Borel sum, but I didn't tell you the resolution of the problem yet. Okay, but go ahead.
Can we apply this Borel transform method only when the perturbation series diverges as a factorial? Like you had a Q factorial dependence.
Yeah.
Right? So for non-such series, can't we apply this method?
Oh, I took Q factorial, and it has this Q factorial has a specific name. It is Jevry 1 class. It can be some power of Q factorial to the power something, okay? Q factorial to the power L. So these things are called Jevry L. And, and those things arise as well. I took this example because it's most generic case. But the Jevry 2 also arises. Maybe in string theory it arises.
But the Borel transform method is a generic method, right?
It may need slight generalization. I didn't work out myself with the Jevry 2. I will come back on that question in the next class. Okay. It's an interesting question whether you can immediately apply Borel.
Okay.
But
yeah, Mithat.
Good questions. Yes.
I've just been informed that you only have 5 more minutes in this time. So say what you want to say, and then you can pick it up later next time.
Okay, actually, yeah. Maybe I should start this thing because I was hoping I could finish this thing in this, but let me start this thing and take 5 minutes, and it will tell at least the young students that there is some geometry behind all of this discussion, and then it will encourage them to think in different terms. So this was the story of the Borel resummation. Now, actually, one can deal with, I will describe the geometric perspective on Borel resummation, but first I need to discuss saddle point method properly, okay? Let's say you have an n-dimensional integral of this exponential type, and the action depends on x1 through xn, okay? So what do? We first find the set of critical points. These are the points that, derivative of the action vanishes. So to each critical point, we associate a cycle. In one dimension, this is called steepest descent cycle or stationary phase cycle. But so more generally, in multiple dimensions, it's called Lefschetz thimble attached to each cycle. Okay. Now it turns out that these cycles will form a complete basis over the space that you want to do integration. So you can write an integral over sigma, whatever you want to do, just in terms of these cycles. This is very interesting. And these cycles are piecewise, smooth, and continuous. Okay. So there is a fancy name for this decomposition. It's called homology cycle decomposition, but it's not very important. I will show you a concrete example. So the real dimension of this cycle is n. So the step 0 of semi-classics is actually make this x1 through xn, xi to a complex quantity. So if you start with Rn, for example, you turn your space into Cn, but then you want to do an integration over half of this middle dimensional space, middle dimensional space. And actually these Lefschetz thimbles have real dimension n, just like Rn. Okay, so so there is a complexification at the first stage, but there is no doubling of the degrees of freedom because you are still doing integral over middle dimensional space. How do you find these cycles? So these cycles are found by solving some complex version of the gradient flow equation. So this tau is a fictitious time, gradient flow time. So you solve these equations, dz over d tau, ds over dz bar, etc., and you solve these equations. And so one thing you can show that if you look to imaginary part of the action, which is the solution of these equations, you can show that the imaginary part of the action remains invariant. This is imaginary part at the critical point is same as imaginary part throughout the whole cycle, the whole thimble. So this is one reason that this method is sometimes called stationary phase methods. And the real part is ever increasing. That tells you that exponential of minus s is ever decreasing. So this is the reason that this path is also called steepest descent path. So if you choose the cycle of the integration by using these gradient flow equations, then the integrals here are actually guaranteed to converge. Okay? So far, everything is exact. And I just want to show you one very simple example. Okay, for example, this exponential integral, it's Gaussian plus a quartic term. Okay. And I will take theta to be argument of w. And I will play with the analytic continuation of this W, make it slightly negative, okay? So you see that this has, the derivative of this is a cubic polynomial, so it has three critical points, here, there, and there, okay? So you can determine steepest descent cycle. For example, for 0 critical point here, the steepest descent cycle is this one. And these blue regions are the regions that you are guaranteed to have convergence. If you start here and end up in another blue region, you are guaranteed to have a convergent integral. For example, this cycle, J1, passing through row 1, starts here, goes to there, from B to C, okay? Now, I will tell you something rather striking. For example, if you want to go from A to C, this is the path, okay? B to C, this is the path, steepest descent path. A to D, this is the path, okay? Now, let me go directly to an example because you told me I have very limited time. Let's say you want to go from A to C here, okay? And make this a bit larger, and steepest descent path at theta equals 0 minus is like this. Let's start with theta equals 0 plus. It is still like this from here to there. Now, as you change theta, this path will deform smoothly like this. We'll start here. We'll start here, we'll do something and end up there. But if you approach theta pi over 2 minus, okay, you want to go from here to there. You see that you can still go from here to there. This is your integral from A to C, okay? And there is a one path here. You go from here to there, okay? But when you cross pi over 2, theta is equal to pi over 2, go there. You see that the cycle J0 here does no longer goes from A to C, okay? There is no direct flight from A to C. If you start from A, okay, if you want to go to C, the only path you can write down is this thing. Then you have to take this flight and you have to take this flight. You have two connections. So it's 3 flights, okay? So you see something very interesting. So first of all, this path here actually changes dramatically, J0 path. There is actually 2 discontinuities in the problem. This thing, okay, let me mark these things differently. This thing jumps. It was this path and it became this path, okay? But you see that the coefficient of J1 and J2, this is another jump, okay? These coefficients here also jumps. So there are 2 discontinuities in the problem. Let's say you want to do this integral from A to C at theta equal pi over 2 minus and pi over 2 plus, okay? If you do this, you see that there are actually discontinuities in the problem, okay? Now let me summarize the end. So each cycle is piecewise continuous, but this theta equal pi over 2 is a Stokes line, but it is discontinuous exactly at the Stokes line. The coefficient of each cycle is piecewise constant, but it is also discontinuous at the Stokes line. So number of active saddles changes when you cross Stokes line. Here, to go from A to C, here, only 1 saddle contributes, but here, to go from A to C, 3 saddles contribute, okay? There are really 3 saddles that contribute, okay? Sorry. So these are the Stokes line. I told you one of the Stokes lines at pi over 2. So you see that there are 2 discontinuities in the problem. But
the combination of two discontinuities is to make the ultimate integral continuous. This is the, I think, brilliant realization of Stokes. And it tells you that actually in these asymptotic divergent series, these are actually exact coded representations of exact functions. So they are well defined under analytic continuation. The function, this integral that I am telling you, can be done exactly, okay? And it's a continuous function at theta equal pi over 2. But the way we describe it in perturbation theory and via semi-classical techniques uses tools such that there are discontinuities in the discussion. There is a discontinuity in the cycle. There is also discontinuity in the coefficients. And the combination of the two, however, is continuous. Okay? This is the beautiful thing in the ordinary integrals. And this is a perfect stopping point for me, okay? And I can take over from here in the next class. But it tells you that probably I will tell you in the next class that, for example, I am telling you that this cycle here has a jump crossing theta equal pi over 2 from here to there. Actually, you can actually calculate what the jump is. And you will realize that it is some, again, imaginary part that changes, but the integral over these two cycles, you know, J0 pi over 2 minus and pi over 2 plus is actually related when we discussed this in the Borel plane. If there's a singularity somewhere, to go around it this way or that way. What I am telling you is that these integrals over the steepest descent cycles is related to integral over these Lefschetz thimbles. So over these steepest descent paths. These two stories are connected to each other. I give you some food for thought.
Can you pick up on this in the next lecture?
Yes. I will restart again from here.
Okay, that sounds very good. Can I ask you a quick question, or I think it was what you're saying? You have an exact answer, correct? And so you actually know the function of W.
Of course.
And that
this function, yeah.
It's just a known integral. I mean, whether you write it down analytically, it doesn't matter. It's a function of W. Is it an analytic? Is it an analytic function of W, or are there singularities in the W plane as well?
It is. I think in this case, it's an analytic function of W.
Right. So I mean, one way to define this, you know the answer. You do it for W where you know it.
In this case, you know the answer. Yes.
Right, and then then you can analytically continue it anywhere, and that's a common thing. So now you're saying that as you tried to analytically continue in W, you have to push the contours around. I mean, this is used for all kinds of special functions, right? In order to write it as a new integral. So what you're doing is you're relating the analyticity in W to the need to define new contours.
What I'm describing is how the contour deforms as I change.
So is this a general lesson, or is it very special to this example?
As far as we understand, this is a general lesson.
Okay, even when you have multiple integrals.
Yeah, multiple integrals. Yeah, this is the general lesson. Actually, between these contours and the Borel plane is like one-dimensional plane, but the very interesting thing is following. Stokes phenomena, even if you do it in multiple dimension, it is a codimension one effect. So this story I told you earlier in this Borel plane, as you go from for example, one choice of cycle to another choice, okay, is a realization of the Stokes phenomena. Here, the integrals are also one-dimensional in this specific example, but because of the fact that Stokes phenomena is a codimension one effect, this story I am telling you on the Borel plane is actually a realization of the Stokes phenomena. It is, in some sense, sometimes it's called stratification, but it's a fancy name for something. So, yeah.
What is it called?
Stratification, stratas. So it reduces this multidimensional field space to this Borel space.
On this before we go to.
You don't have to worry about. You don't have to worry about it. But if there are questions about this,
we can pick them up in the next lecture. But are there any questions right now where people have something in their mind? Going once, twice? Yeah. Okay, so we're going to take a break, and thanks a lot. It's very interesting. As I say, you know, any convergent integral is a function of parameters defines usually analytics domains for the parameters. I mean, that's a general theorem, right?
Yeah, these things, when we describe them in perturbation theory in terms of semi-classics, are always described in terms of these cycles. And,
yeah, I understand.
You know,
I understand. That's yeah.
I think it's a very interesting story.
But at least you know the answer that you're trying to shoot at, so that it takes away the ambiguity.
Yeah. But even in some infinite dimensional integrals, we know that this story works either in quantum mechanics and quantum field theory. There are many examples now.
Thanks a lot.
Okay, sounds great. Thank you. Bye-bye.